Hi, I'm Qing. I'm a current assistant professor in ECE. And today I'm going to change my topic a little bit to better fit this symposium. So I'm going to talk about something on generative AI, and we're going to focus on more scientific and engineering problems. So to give you a little bit background of my group, so my interest is on foundations, mathematical foundations of generative AI models recently. I work on optimization, serial machine learning, and inverse problems. And more recently, I'm very interested in AI for science. And I have a group that working on diverse topics in this area. So recently, I'm very excited about this generative AI models, right? And the generative AI models actually started just around 12 years ago. So from this variational autoencoder, and if you look at visions in images, like generating images, right? We have VE to GAN to more recent DALI and Sora models, and for language models, we have transformers, right? Clip and the ChatGPT moment and ChatGPT-4, and more recent DeepSeek models, right? So my group is working trying to improve the interpretability, efficiency, and the controllability in the past. And the core idea of doing this is that actually the data and the model often have some low-dimensional structures, and we're going to leverage these kind of low-dimensional structures in data and model to make them more interpretable, more efficient, and even we can control the generation process of those models. And my group is working on theory and computation. But for today's talk, I'm not going to talking about this because I think I want to show you some examples where I can leverage this kind of methods we developed and this kind of idea we developed to apply them to scientific applications. So how can we leverage the generative AI models that we developed to tackle scientific problems across engineering and science? And I'm going to through three examples that we have some interesting results that I want to share with you. So the three results I want to share, one is a scientific computing problem, which is a data assimilation problem that has many applications. And then I'm going to talk about generative AI safety and this kind of sim-to-real sensing problem in engineering. So first, I want to start with this data assimilation task. So the basic problem setup is the following. So here we are going to predict a stochastic dynamic system. And here our task is that our data, so X is something we want to predict. It's governed by a stochastic dynamic system where we have some state transition map which might not know or know ahead. And this task is quite difficult. So here we consider a setting where we have partial observations for the X, right? So for each state of X, we have some partial observations where this A operator is something that we are measuring a partial observation of our X. This can be like a sparse measurement, or it can be a low resolution measurement of our data. And our goal here is that we are given the observation wise, we might not know the state transition. We have some perturbation, psi and eta, which is a noise injected to a system that we don't know. And our goal here is that we want to estimate the state transition and we want to reconstruct our X. So this is a called data assimilation problem where we want to combine observations and with numerical models and methods to improve the prediction in complex stochastic dynamic system. And solving such a problem has many scientific applications, like earthquake prediction, weather forecasting, and hurricane predictions. And this kind of problem appear ubiquitously in science and engineering. But the question is, how can we solve it? And actually, the idea here, there's some classical methods to solve it. For example, there's a common filter that can track the states of the dynamic system. But the classical common filter, they assume that the state map needs to be a linear map, right? And if the state transition is not linear and the noise is not Gaussian, actually the Kalman filter will break down. And More recently, another classical approach is the particle filter, right? You can use particle filter to track the stochastic dynamic system. But the thing is that particle filters, you need to simulate the particles and suffers from this so-called curse of dimensionality, right? If you solving low-dimensional problems using particle filter is good, but it's too expensive when we're solving modern scientific problem where the problem is very high dimension. And more recently, people are digging into this data-driven method. And one particular method of interest is using this diffusion model or generative models that I mentioned previously to solve the problem. So basically what diffusion model is doing is that we're going to estimate the joint distributions between all the states, like say X, all the X, right? We want to estimate the joint probability of all the X. And this is a plot of the confidence interval for each state estimate. And I think the diffusion model, the challenge here is that it haven't utilized the state transition map. It haven't have a very good way to estimate the state transition map between states, right? They just treat each state individually and estimate the joint distribution across all the data. So the performance is actually not so good. If you look at the confidence interval, right, it's very large. So in our work, we introduced a new method, which is called flow DAS. So basically, it's using a new type of generative models, where instead of estimating the joint distributions across all the data, so what we are doing is that we're going to estimate the state transition between the data points, right? So in other words, our method is not estimating the joint distribution, but we are estimating the state transition map between each state. And once we estimate the state transition map, we can do the state estimation using autoregressive in an autoregressive way, right? So say if we estimate one state, and then we're going to predict the future states in an autoregressive manner, right? Just to follow this kind of state transition map estimation. And if you look at on the right-hand side, right, because we are estimating the state transition instead of estimating the joint distributions, and we know that for the stochastic system is governed by the same state transition, right? And that's why actually our prediction is much better. And then we can estimate the future states using an autoregressive manner. So, and that's why actually our method, although there are error propagation in the future, but our method is much more accurate. There's a... Sorry, my microphone's cut out. Yeah. Okay. Yeah, so you can see that the confidence interval is much smaller. And the basic idea of our algorithm is that we're going to say if at state xk, right, we're going to estimate the state transition from xk to xk plus 1. So what we're going to be doing is that we're going to use a method called stochastic interpolant. So we're going to use a method called stochastic interpolant that we are going to estimate state transition from xk to xk plus 1 hat prime. And then based on that, we are going to do a corrector. Remember, we have some measurement. We're able to leverage the measurement y to correct our estimation to predict our next xk plus 1. And when we estimate this, then we're going to estimate all the future states using autoregressive method, right? We're going to estimate the next iteration by repeating the process that we talked about previously. So this is a basic idea, and this is our algorithm for our so-called flow DAS method. And we test our method from low-dimensional problems to high-dimensional problems, and it shows much better result compared to setup diffusion type of models. So first, this experiment is that we're doing the state estimation for Lorentz systems. And this is a low-dimensional problem, so this is a three-dimensional problem. And this is our system dynamics, and we have observation which is measuring the first coordinate. And this is the result we get, right? So this is the flow DAS method that we introduced. If you compare to the particle filters and the diffusion model-based SDA method and some recurrent neural networks. So you can see that actually our method is working very well compared even to the particle filters, where the particle filters knows the state transitions ahead. But our method doesn't know the state transition. We're going to learn the state transition from our data. And this is another result that we tried on some high-dimensional problems with narrow Stokes equations. And if you compare our method, and this is our method called flow-DAS, we tried on both super-resolution task and sparse overlation task, and you can see that actually our method is getting better performance than the diffusion SDA method. It's better matching the true states. And moreover, we also plot the kinetic energy spectrum, and we can observe is that our method is working better in the high-frequency component, predicting the high-frequency component compared to the existing method. And finally, we also test on some real applications. So this is a collaboration with my collaborators, and we tried on this PIV task, which is a device that is used for measuring the velocity field in many scientific applications. And what we show is that actually by using the flow-DAS, our method, actually, again, we can achieve better performance compared to the existing diffusion model-based method. And this is a result showing on this super-resolution task in PIV. So this is the first project we've done. The second project I want to briefly talk about is this AI safety, right? We want to guarantee, so our modern, generative models, although they are very powerful, right, but they can generate harmful content, and how can we prevent that? So in the past several years, right, we've witnessed this powerful like DALL-E model or this text-to-image generative AI diffusion models, right? If you give them some text prompt and they can generate some realistic images, something like this. So this is very powerful. You can just give some text prompt, they're going to generate images like very realistic. But however, using these kind of generative AI models could have some safety concerns, right? For example, if you look at the generated image, like say if you have a training data, this is an image woman in the training data set, and you have her name here, right? And when you train the model and you try to deploy the model, the user, given the name of the woman, and they're going to generate some images pretty close to the data in the training data set. And also in generative models, they're going to learn some certain patterns in the data, and they might infringe the copyright, right? And finally, it might also like generate something harmful, right? So it's kind of a nude woman, like if you trigger them by some harmful text prompt. So there's some concerns about the safety using the generative AI models. And so that's why actually we want to do something called machine learning. So basically we're given like a model, we want to remove this kind of harmful content from this kind of pre-trained model, right? We're going to remove this kind of like copyright fringe privacy issues, like memorized data in the training data set. And what people do in practice for machine learning is that they're going to fine-tune the model on the harmful content and to remove the harmful content. So for example, we can fine-tune the model on the pre-trained model on harmful content to prevent the model to generate this kind of a nude woman, this kind of flying girl style for the copyright fringe, and we can remove the object from the data. But however, this kind of unlearned model actually is not very robust. So this is an illustration here. So say you have a model that has been unlearned by fine-tuning them on the harmful content, and you are able to simply jailbreak those unlearned model just by adding some adversarial text prompt to the prompt you trigger this kind of generation. And this is an example, right? You just add some like adversarial tags to the text prompt, and then you're going to generate the nude woman, the find out style, and object again, right? You're going to jailbreak the model. So this further raises some concerns about the safety and robustness of those models. But however, existing jailbreaking methods, actually, they are not very interpretable, right? If you look at the adversarial text prompt that you attached to the original text, they are not very interpretable, right? You don't know what kind of a text you trigger this kind of harmful content to be regenerated again. So in our work, so what we are doing is that we introduce a new method where we are going to add to attack the unlearned model in the token embedding space. And we're going to enforce certain linear structures in learning such adversarial attacking on the unlearned model. And the benefit of enforcing linearity and enforcing this in the token embedding space is that we can make our model, a method, more interpretable, more robust, and also leading to robust defending method. So next I want to show you some result. So here is a result of our method, right? So this is our result can trigger like the jailbreak our model to regenerate the harmful content and nude woman and fringe the copyright again. But we are not significantly distorting the image comparing to the state-of-the-art CCE method, which is trying to jailbreak the unlearned model. But we're going to distort the image. For example, the background has been changed in this case. And moreover, our method is more interpretable, right? Here is the text token, the token embeddings that we identified in the model that trying to attack the nude woman. For example, when we're attacking the original model, right, we're going to find the text that is more corresponding to, like, say, nude, bare, and naked, right? When we are using our method to attack unlearned model, we find that the token embeddings that actually are indirectly related to this nude concept, right? For example, the sleep, the nip, and the scan, etc., right? They are not directly related to the concept, but actually they are indirectly related. And that's why identifying this kind of an indirect concept triggers model to regenerate the harmful content again. And finally, we can inspire defense of this kind of adversarial attacks. So basically what we can do is that once we identify the token embeddings, the harmful token embeddings, we're going to do orthogonal projection. We're going to project this kind of harmful content out from this token embedding space that can help us to defend our model. So I don't think I have time to cover the final part, which is for the safe to real learning, that we can solve inverse problems using large language models to adapt to different scenarios. But I don't think I have time to cover those. I'll just skip. So finally, I want to thank all the funding agencies and my students for doing this line of research, and I would welcome any questions. Thank you.
Another historical comment. We've had generative models since the 1960s. It's not a new idea. It goes back to Chomsky's notion of generative grammars and work on grammar induction, but also probabilistic, like Markov models, that are really an early version of what you find with the new neural net approaches to language. So not a new idea. I think it's and of course Bayes-nets were always called generative models. So it's a misnomer to say that generative AI is a new thing.
Okay.
Certainly it's a new technology, but we have to be careful about what we call it, or at least saying it's new. But I have a question about your the equation stuff you talked about. There's a long line of work on discovering equations by searching a space of equations, both for static data, but also for finding differential equations. And I'm just curious why you were using the method you did, rather than, say, defining these, like Mario was talking about, define a space, search the space constrained by the data, and when you're done, you know that you have something that's going to be interpretable. Did you consider that approach?
So are you mentioning to this the first part I talked about, this part, the data dissemination task?
Well, maybe you were doing that and I just didn't get it. So what is the space that your system was searching?
So we are learning these state transitions between different data points, right? We're learning the functions here.
So the space that the system is searching is a space of equations, or is it a space of parameters that can be turned into equations?
The state is equations. Yeah.
You're searching a space of functional forms.
Yes. Right.
Very good. Okay.
Yeah.
Well then that's great. Join the club. But we've been doing. We ran a couple of AAI workshops on this. A bunch of people coming from physics and mechanical engineering who have been doing this. But there's also older literature of people who use sort of classic symbolic AI techniques too. And so I'd love to talk to you about it and point you.
Sure.
But carry on.
Sure. Thank you so much.
Two questions, somewhat unrelated. So the first is, you begin with image, but these seem to be reflective images rather than projected through a volume. So I'm thinking of a planar X-ray, which many people call an image, and a photographic plate, which is a reflective image that gives you no information about the density of the object from which it went through. So do you have an ontology in terms of what you mean when you say image, or are you just ignoring the projected image concept in what you're doing here?
So here, so for this kind of, so for all this task we test here is images. So here we're basically essentially learning the prior of the data to reconstruct those images.
What is the original prior? Is it a reflected image back to a plate of a light coming back to a collection plate, or is the collection plate behind the object in which you are transmitting the photons through? They're very different conceptual outcomes.
So here, let me see. So for this example, that the image X is the object, right? And then actually the measurement Y is the image system, right? The photons passing through it, and then we're going to based on this system, right? We're going to recover the X, the ground truth image there.
I'm sure that we're communicating, but that's okay. The second issue is about the use of the word safety.
Yes.
So I personally, and I'm speaking only for myself, have a concern about the fact that the changing of these isn't a safety issue, it's a conformance to authority, and that it's stripping away valuable information in order to conform with, I think, mostly big industry, which is concerned about not offending people or getting kicked out of the EU because they've offended GPR domains or whatever. I do not appreciate the idea of covering up nudes because it conforms to authority. I worry that that kind of leads you down a slippery slope away from getting valuable information, and that you have, in a way, dehumanized the data and stripped away valuable conceptual domains that are now removed from the data for future activity with it.
Yeah, so I think there's 2 points, right? So one is definitely we need some regulation because, for example, there are some privacy issues. If you user doesn't want to release their privacy issue, right? We can run into some like lawsuit, right? So, but we need to be selective, right? There's certain information needs to be removed, right? But there are other like information we should preserve there, and that's why we want to to be selective, we want to do machine unlearning, we're going to like unlearn only a very few concepts from the data, but from the model, but we want to keep the other concept that is unchanged in the generation process. And we want to like be selective here. Yeah, and that's how we'll go.
I agree.
Yeah.
That's why I'm concerned about more concepts saying I think they're doing the exact opposite.
Okay, thank you. Yeah.
Hey, good morning. Could you go back to like the first couple of slides you had? The first couple of slides, if you go back.
Oh.
I had a couple of questions related to that. So just to give you some background, I'm working on a order forecasting system. So that's kind of, just to kind of give you some background so you can help kind of align to that a little bit. So I had trouble understanding like from this slide to your next slide. You talked about models here. So were you talking about from like a classic machine learning models point of view or something else? So this is the first question. And the second question is the DAS model that your team works on. Is the conclusion that for forecasting type applications, that model, the one your team works, is more effective compared to some, you know, like a multi-layer networking or LSTM or something like that? So that's my two questions basically. If you can kind of provide some more context, I'd appreciate it.
So your first question is about the classical approach. Like if you solve the data dissemination problem like this, so your question is about why we are introducing this kind of a diffusion model to compare to the classical method. Is that your question?
No, I couldn't really understand, like when you said model base, were you referring to like classical machine learning model base here or something else?
Oh, so the model base is that here, like for Kalman filter or particle filter, they need to know the state transition model. So this is the model is know ahead. But for our method, right, for this like state of diffusion have also method and also our flow DAS, we don't need to know the state transition. We're going to learn it from the training data, and then we're going to generalize it to new tasks and do predictions.
Yeah, so from my point of view, I'm like I'm familiar with the Kalman filter a little bit, but I don't understand like the state transition. So that's why I was asking like what I was trying to align that to like the classic machine learning model. So is there anything to do with that, the state transitions? So I actually don't understand what the state transition is. So that's why I kind of was trying to ask what this model.
So a state transition is a map that is mapping from a current state to the next state, right? For example, if you look at this Lorentz system, right? So you can view this is your state transition, right? So this is a coordinate x1, x2, x3, the coordinate, and it's governed by this system dynamics, right? If you have a current state, and then by this ODE equations, you're going to generate next state following this state transition.
So would like a state transition would be like, you know, if you have like historic data, like, you know, like from week 1, so week n to n-1, would that like a straight transition in that sense? Is that correct understanding?
Yeah, you can interpret it in some way like this, yeah.
Okay, so for my second question, like, does this DAS method, is it more effective compared to these other?
Sorry, which gas method?
The method that your team worked on, the flow DAS, I think it was. Is it more effective than other machine learning models from a?
Yes, so far we compared with the state-of-art method, like the flow DAS, for example, which is a data-driven method. We want to learn the state transition. And this is a very simple illustration, right? If you look at the SDA, right, the confidence interval for each state estimation or state prediction is pretty large. But if you look at our method, because we are estimating the state transitions, and the state transitions are the same for each state, right? So actually our method is working better. We have a smaller confidence interval compared to the SDA. And also, if you look at the result we get for the even on the low-dimensional problem, we are almost matching the particle filters where we know the state. But here, we are learning the state from the training data. We don't know the state, and we're going to almost achieve comparable result to particle filter. But if you look at all the learning-based methods or data-driven methods like using diffusion models or RNNs, LSTM method, right, the performance is not that good, right? The estimation, the state estimation actually have some large errors.
Okay, thank you so much.
Okay, thank you.